So this week we're going to talk about physical and virtual computing, or what I like to refer to as computing architectures, as we're not necessarily going to talk about how, um, you know, exactly, the bits and bytes of everything, but we're going to talk about, how computers were designed and kind of the processes by which computing happens. And so we'll talk a little bit about those which I like to refer to as architectures. So to give you an overview of what we're going to talk about, in this section we'll discuss different types of computing resources. First we'll talk about the basics of physical hardware. I do this so you have an understanding of how basic computers actually work. How many of us really know what goes on under the hood. So we give you an overview of that and some very simple ways to talk about, for example, the von Neumann architecture, by which most processors are modeled after. So we talk about how basic computers work. Then we discuss how these computing resources are virtualized. So how things work currently in work environments is that there's not necessarily a one-to-one relationship between the physical hardware box and the number of computing resources you have. Because they're what's referred to as virtualized. So literally multiple computers can run on a single physical computer, if that makes any sense. And we'll talk a little bit more about that so that hopefully it does make sense. The different types of virtualization, we'll talk about that. We'll get a little bit into the nuts and bolts of what virtualization means. And we'll talk about how computing resources can be distributed to enable massive parallel operations. And so from the ability to virtualize and massively distribute processing comes this idea of cloud computing. And what we do is go through the ontologies of cloud computing, the different classifications of what cloud computing is and its many different incarnations. So let's proceed to the next slide, and let's first talk about physical hardware. So the physical components, we're going to talk about the physical components that perform basically the following activities. Input, the input of data, how that data is processed, where it's stored, both in the short term and long term, such as where it's being stored while it's being processed and where it's being stored after it's processed, where that goes, and the resulting output. Those are the basic components that perform, we'll talk about the basic components that perform those following activities. So, physical systems that are built to respond to the analog world. They're inevitably designed around the limits and expressions of the human body. These are basic components of physical hardware, right? They're not designed for other computing in a lot of ways. Originally they're designed to enable how humans work, and so this is also one of the basic definitions of information systems. And I put it here to kind of talk about why physical hardware is how it is that at a very basic level, information systems or information technology, physical hardware in other words, it mediates human communication through the concepts that begin right here at this level. So let's go to the next slide and talk about hardware components. And the number of components we're going to talk about here are the arithmetic logic unit, the control unit, and registers, as well as different types of storage, such as primary and secondary storage. So the ALU, the arithmetic logic unit, the control unit, and registers, those are things that are within the scope of the processor. And I have a diagram here which kind of gives you a little bit of a pictorial of the von Neumann architecture, where you have a control unit, an arithmetic logic unit, and a register storage area inside the processing device, and then it also includes a separate block and considers that part of the processing device is the notion of primary storage or memory. And so then outside of that processing device you have secondary storage. Now, as we'll also explore, primary storage has a number of different incarnations, and we'll talk a little bit about those in the next few slides. But first we're going to talk about computer processing. and the automated methods to process data, as that's effectively all that it is. Computer processing, as complex as it may seem, is just the assemblage of a number of different very simple tasks. So computer processing at its most basic level is just simple repetitive activities that process large amounts of similar information. A process is an instance of a computer program that's being executed. It contains program code and instructions about current activities. Based on hardware and operating systems, these processes may be actually executed concurrently. And so, many times they're measured by machine cycle time and clock speed. And there's a very important theory about how that increases, which is called Moore's Law. Basically, it's a theory about how fast machine cycle time and clock speed increase with new hardware. And it pretty much states on average, it's a little bit more theoretical, but it kind of manifests itself in this way. It states on average that average transistor densities on a single chip double about every 18 months. And that law has proven to be pretty accurate over the last 30, 40 years since Moore came up with his law. I don't know too much about Moore, but I know that law is about 30 or 40 years old. Pretty amazing theory that he came up with, and still very widely applicable. So let's go to the next slide and talk a little bit more about how computer processing works. So to explain this, we'll use the LMC model, the little man computer. And so it's just a very, very basic way of talking about how memory is taken from one place, processed, and goes to another. So, to execute a program, the little man, quote unquote, performs these steps, right? Checks the program counter for a mailbox number that contains a program instruction, like the first instruction. It gets that instruction from the mailbox with that number, increments the program counter so that it contains the mailbox number of the next instruction, the next one that has to go through the pipeline. It decodes that instruction, finding the mailbox number for the data that it will work on. For example, if it gets data from box 42, then it fetches that data from that mailbox with the number found in the previous step, and then executes that instruction. Then stores the new data in the mailbox from which the old data retrieves, and then that cycle is either repeated or halted for a number of different reasons related to processing. Maybe you turn the computer off. That could be one. That definitely halts processes. Or you're shutting the computer down. That causes a halt and pauses things where they were, and potentially, depending on how your computer is set up, continues to repeat those cycles. Whether it's something that's more application driven or something more internal to the works of the computer, those cycles get repeated when the computer boots back up. So let's talk about different types of processing on the next slide. So in today's computers, processing is rarely done as a single activity, like, little man computer instruction, 1 through 7, going through 1 through 7, going through 1 through 7, as a single stream of activities. Instead, what happens is, because of physical hardware and the way we've been able to compress physical hardware down, there's usually multiple cores or processing units to a CPU, and sometimes actually multiple CPUs. So you can have dual or quad-core processors, which I'm sure you may have heard of. For example, the laptop that's recording this presentation has a dual-core processor. And then some bigger towers, actual hardware, bigger servers or desktop computers have quad-core processors. Like I think the iMacs, the current iMacs have quad-core processors. The current desktop Macs. And so with those additional cores, there's additional memory that's located really, really close to those cores, so that there can be quick access to those things, as quick as humanly possible, so that it slows down things as not humanly possible, as machinely possible, I guess, so that it slows down things as little as possibly can, so that you can process things in parallel. Collectively, these are known as multi-core processors. These things that we see in most of our laptops today, if you have a recently bought laptop. So part of this multi-core processing architecture is the notion of specialized processors to process specific types of instructions, and we call these coprocessors. A very common type of coprocessor is a math coprocessor, which is specifically for mathematical operation. So in general, the general definition or meaning of multiprocessing is that it's just two or more instructions that are executed at the same time. It's the very basic meaning. And then in the above bullets, this is the last bullet. In the above bullets, we kind of give some examples of what this meaning of multiprocessing, how it actually takes form. So we've talked about, you've given a little bit of input on processing. Now what we're going to do is we're going to move to the notion of memory and talk about what memory is, kind of in its more definitional sense, different types of memory. So the memory we're specifically talking about here is primary memory. Now, I'll make a quick clarification on terms. There's primary memory, which I'm just calling memory at this point, and then there's secondary memory, which I'm going to call storage. So there's memory and storage. You can also call them primary memory and secondary memory. Your call. The two terms are synonymous with one another. Just know that when I give an exam, if I call it one thing, you're going to have to, you have to be familiar with both terms. And as they're both widely used in industry, it's generally good for you to be familiar with those terms. So, we'll talk about primary memory. And what primary memory is just physical devices used to store programs or instruction sets and or their related data. So it's usually stored on what we refer to as volatile memory, a temporary basis, which requires power to store that information. It's usually organized into memory cells that have an address and can store a single bit of information in each one of those addresses, though different types of memory are configured differently. So you have to, there might be differences. But in general, that's kind of the general theory of what a memory cell does within primary memory. So it's also, I've talked about this, it's different from storage. Secondary memory, which stores information indefinitely. So let's talk a little bit more about the different types of memory. So registers, right? That's one type of memory that sits the closest to the CPU. Registers are tiny, tiny little bits of memory that only store, maybe a half a byte or a byte of information. So tiny, tiny little bits, maybe a single character, or not even that much. Maybe just storing things, maybe just storing bits of information, or where it's measured in bits. So it's just a small amount of storage available as part of a CPU or other type of digital processor. Another type of memory is cache. And so cache, a register can also be considered cache. There can also be what they refer to as level 2 cache, whereas a register might be considered level 1 cache. There's also level 2 cache, which also sits very, very close to the processor and has a specific purpose of storing data so that future requests for that data or of a similar instruction can be served really fast. Another type of memory, one that's replaceable, for example, in the laptop that I have that I'm recording this presentation on, I can upgrade, is the notion of random access memory, or RAM, which are just devices that allow stored data to be accessed directly in any random order. So it's another piece of primary memory that's not within the actual CPU unit. In older desktop units where you could build your own thing, you would put in RAM and then you would put in a processing unit. Whereas you couldn't put in your own registers or cache because that stuff was usually soldered on to the actual board that had the CPU that did all the processing instructions. So those are the differences there. So many of you have probably heard of random access memory, but you might not have heard of its cousin there, read-only memory, which can only be modified slowly or with some difficulty. So it's read-only. It's actually usually where your operating system is stored. Usually the operating system is stored in non-volatile, memory where if you power it off, it doesn't matter. It stores it in a special place called read-only memory. That's usually also soldered on to kind of the motherboard of a computer. So it's there to store things, for example, like the operating system or other critical pieces of information that aren't expected to go anywhere anytime soon. Maybe when you upgrade your operating system or upgrade or have major bug fixes, it upgrades parts of read-only memory. So I also list some other types of memory which we're not going to get into, specifically other types of RAM, such as dynamic RAM or static RAM. You're definitely free to look those up, but we're going to be more concerned with the overall definitions of different types of memory. So let's proceed to the next slide, where we talk about how memory actually works. So I try and drum up a pretty simple example of how memory actually works, and it's a lot of times very directly related to the LMC model, the little man computer. But let's kind of back that instruction set up a little bit with a little bit of deep dive on how memory works. So let's give a really simple example. Let's say you are the CPU. You're the guy or girl who does some processing. Then you also have your computer desktop is the memory, and your computer desk drawers are the hard drive. And let's say you have one layer of stuff. Right? You're only allowed to have one layer of stuff on the desktop, on this physical desktop that you have. Let's say, for example, you have a bunch of index cards, and you're not allowed to have any overlapping index cards. So you only have so much usable surface on the top of the desk, and it's consistently being cleaned off. And so, for example, you have to go to the memory on the desktop, which can be registers, cache, or RAM. This very fixed memory. And if what you want is not there, then you have to go to the drawers. So this example aligns to this hierarchical triangle that I have on the right, where the processor wants to go to the quickest forms of memory first, so that it takes less time to process tasks. Right? That's kind of the meta task of the processor, is take the least amount of time to do whatever it needs to do. So first it goes to the registers, then it goes to caches, and I have level 1 cache, level 2 cache, which can or cannot be considered a register. Then it goes to RAM, physical or virtual memory, and then it goes to what it's saying there is that RAM can be stored, RAM can be physical. It can be something you upgrade your computer with or have as a stick inside your computer. Then it can also be virtual. There's the old Windows machines actually take portions of the disk drive and use it for random access memory. There's a problem with that. Virtual memory is really slow compared to actual primary memory. So it can be quite problematic if you're using virtual memory for too many things. So, and then you've got other types of memory, which are down in the storage device area, such as read-only memory, your basic input-output system, removable storage drives, internet storage, and your own hard drive. And then, of course, your input sources, that actually put data into these things for one reason or another. So that gives you a little bit of an insight of how memory works. Now let's take a look at, let's start to gravitate some of the basic concepts here and talk about parallel computing. Related to multiprocessing in some ways, this is where we spread the distribution of tasks not just across different CPUs on a single machine, but different CPUs on multiple machines. So parallel computing is simply the simultaneous execution of the same task on multiple processors. This helps us, do things faster, right? That's the number one reason we do parallel computing. It, helps us take large problems and divide them into smaller, discrete chunks, and solve those discrete chunks concurrently, and then bring it back into a, ultimate solution. Right? At some point within parallel computing, there are things that do more higher level tasks and things that do some of these more discrete tasks. And so you also have the notion of grid computing, where there's a very formal schedule or coordination to some of these tasks. So let's move on to the next slide, which takes the notions that we've learned so far of the physical aspects of computing and how to take multiple physical blocks in terms of parallel computing and spread the execution of tasks across these physical hardwares. And now let's take that and let's gravitate it towards the notion of virtual computing, where virtual computing takes this concept of physical hardware and having a single operating system on a single box, and now saying that you can have multiple operating systems, different operating systems, on a single box. And that's revolutionary, and that revolutionizes what we're going to talk about over the next few slides after we talk about virtualization with respect to cloud computing. But let's just talk about this notion of virtual computing and what it means. Let's give a little bit of an in-depth understanding of what that means. So, virtual computing is simply an electronic representation of a computer hardware platform. It takes there's a virtual machine, takes an operating system, allows you to run applications on it. It allows you to boot up that operating system and run applications. It can also be a virtual representation of the operating system itself. So there can be embedded virtualization, for example. It can be a storage device or it can be other computer network resources. So this is the notion of virtual computing in a very broad sense. You can have virtual storage devices, virtual communications devices, computer network resources, and then virtual representations of an operating system. And so I just give that first bullet point as a very general definition of what virtual computing is. And those next 3 bullet points talk about give some examples of the different types. So let's talk a little bit more about virtualization types in a more low-level sense, because there's a number of ways that virtualization can take place. So a virtual machine that acts like a real computer with an operating system is known as platform virtualization. And this can take place in a number of different ways. The first is a almost complete simulation of the actual hardware, where there's no layer that has to do a lot of translation between the types of things you're trying to execute on, for example, a virtualized PC or Windows operating system running on Mac hardware. Mac hardware is specifically designed for the Mac operating system and vice versa. So it's possible to run a PC operating system using an application called Parallels on a Mac computer. I do this when we have access assignments later in the semester. Since I'm a Mac guy, I actually have a version of Parallels running that allows me to run Access on my Mac machine, which is a Windows-only application. So, that's more of an example of, let me just say, there's a number of different ways that can happen. It can happen through full virtualization, where you have an almost complete simulation of the actual hardware. Potentially full virtualization can be faster. You have partial virtualization, which is somewhere in the middle of full virtualization, where some but not all of the target environment is simulated, maybe things to make the system most efficient. And then you have the notion of paravirtualization, where programs are executed or run on where guest programs are programs that run on different operating systems are executed in their own completely isolated domains. And with paravirtualization, there's potentially more translation that has to take place. But once again, this all depends. So let's talk some more about virtualization, and give some examples. So here's one such example, and let's take a look at the picture first, where I've basically got 6 different operating systems going on at the same time. I've got an instance of Windows in the upper left, center up, top center, I have the Mac operating system. Top right, I have another Mac operating system. Bottom left, I have Windows. It's a little difficult to see, but I believe that's a Mac operating system in the middle there on the bottom. And then another Windows operating system looking like it's running an older version of Windows XP. I remember that green field. So this is an example of desktop virtualization, which I think is the simplest type of virtualization to understand, because this gives it to you in a end user sense where you can really see the picture there of what virtualization means. This should allow you to explain it pretty well. That picture is kind of worth 1,000 words with respect to virtualization, and as it gives you an example of desktop virtualization. It creates a desktop, quote unquote, of another operating system. So now going to the next slide is server virtualization, where it's basically the same thing, except servers don't necessarily have a user interface. So you can run multiple server operating systems on a single machine, or you can run many across multiple machines. It's kind of like a many-to-many relationship, if you will, as we talked about that stuff like that in databases, where you can run you can have a cluster of hardware, and you can virtualize many different operating systems on that hardware. And it can also be virtualized infinitely. You can run virtual machines inside virtual machines. There's nothing that stops you from doing that. And that's what's known as embedded virtualization. So let's move to the next slide that talks about virtualization architecture. So there's a couple different terms I want to go over so that helps you understand what goes on underneath the hood, how computers are actually able to run different operating systems on kind of disparate pieces of hardware, and how that kind of translation takes place. And then after this, we'll talk about how this notion of virtualization, virtualized hardware, gives rise to us being able to offer these types of things as services in the cloud. So virtualization architecture. The first such term is hypervisor, which is basically a piece of computer software, firmware, or even hardware that creates and runs virtual machines. So in this picture that we have here, the hypervisor is effectively your ESX, what's called the ESX server, and this is a vendor-specific example. There's another hypervisor, open source. It's called Xen. That's a Type 1 hypervisor that can run multiple guest operating systems. But basically, the hypervisor, is kind of acts as a secure manager or secure layer between the hardware and these virtual machines. So, it runs one or more software implementations, and these software implementations are what we call, and I've been using this term, a little bit throughout the presentation, what is known as virtual machines. Think of a virtual machine as something that is a one-to-one relationship that has a one-to-one relationship with an operating system. A virtual machine is basically something that just allows you to run an operating system isolated, regardless of hardware, or not completely regardless, but fairly regardless, since we can run disparate operating systems on single hardware. So, this picture also gives you a good general overview of the different components. At the bottom level, you have hardware, which is the actual. It all boils down to hardware. The actual CPUs, memories, network interface cards, the NICs, and the disks for storage that are actually going to be used by these different operating systems. And then you have the thing called ESX server, which is your hypervisor. And then within it, you've got kind of where the black circle in the black rounded square, within it you have kind of the little icons that depict hardware, and these are your virtual machines. And then running in your virtual machines are the operating systems and applications. I understand this is a little confusing because you have physical representations of hardware and then virtual representations of hardware, and then you have something in the middle the ESX server that translates between these virtual representations of hardware and the physical representations. Now, the virtual representations, the little rounded square that has the little pieces of hardware, in both of the, bigger squares there, right underneath, the operating system. These virtual pieces of hardware are the ones that ultimately agree with the operating system that it's running as a guest. So, if the operating system on the left is Mac, operating system on the right is PC, you've got an x86 architecture on the left, or I'm sorry, you've got an x86 architecture on the right if it's running Windows, and then you potentially have like a PowerPC or maybe more ARM-based architecture, or Mac-based architecture on the left. So if the left is the Mac and the right's the PC. So the point of virtualization is to get rid of the one-to-one relationship. And so what that's done is give rise to the notion of cloud computing, which we'll talk about here on the next slide. Cloud computing is a very general notion, but ultimately, without the ability to virtualize resources the way we're now able to do, we'd never have cloud computing. So cloud computing brings together those concepts. It offers virtualized computing resources as servers in a number of different ways. It offers massive numbers of computing resources over the internet, as services. And you can also share these resources, which achieve economies of scale and lowers the cost of these resources. For example, it's really cheap to buy compute power on Amazon Web Services, which is Amazon Web Services is basically the quintessential definition of all the different types of cloud computing that we'll talk about. And the other way to think of cloud computing is computation as a utility. It's a service, it's a utility, the same way that you can, buy water, trash services, electrical services for your home or apartment, is the same way that you can buy computing resources in the cloud from places like Amazon Web Services, on different levels with places like Salesforce, or other types of places on the internet like Cloud Foundry, which is more open source based, where you can purchase these utilities. You can buy them as a service. So I think what's really important here with the next slide, we're now on slide 18, is to have an ontology of cloud computing, like a classification, to know the different types of cloud computing services that are currently being offered. And this is just at the time of this writing. Might be by the time you get out of San Francisco State that there's different nomenclature or words used to describe these types of things other than what I'm using right now, or maybe different types of services that are being offered. Who knows? So for now, let's look at this current ontology, and let's take the many services of cloud computing and classify them into groups just simply for the purposes of helping our understanding. And so in the current model that I'm using here, this is from a paper published in 2009 in I think ACM Transactions. You have a dependency on layers. And so at the bottom level, you have hardware as a service. Then you have basic operating system kernel. Then you also have different types of resources that are being offered as services above that, such as different computational resources, or data storage resources, communications resources, which is all part of cloud software infrastructure. And then you have the actual environment, which offers platform as a service, and then applications that run on top of all that stuff, which is software as a service. So let's work our way up from the bottom of this cloud computing stack, if you will. And let's first talk about hardware as a service, which is kind of an exception of virtualization, because this actually allows for the allocation of physical hardware. You can subscribe, you can go on Amazon, Amazon Web Services, and literally buy a dedicated piece of hardware. It's actually possible to do that. It's not cheap, but you can actually do that. And if you have a really good reason to, if you really need that direct interaction with hardware, depending on what you're doing. For example, hardcore video processing may need direct access to hardware. So it allows you to do that. You can usually access these services remotely, and it's very useful if you need a dedicated server. Just to give you an example of what exactly this all means, is that hardware is effectively leased for a fixed period of time to a customer. Let's talk about another type of infrastructure or computational resources with respect to infrastructure as a service. So this is where virtual machines are the most common types of things that you'll see with infrastructure as a service. One example, and I've done this many times as a software engineer when I was one, is that I would use Amazon Web Services to spin up a virtual instance of something like Amazon Linux and be able to execute commands against it. You can even spin up a virtual instance of Windows, and using a remote desktop client, you can log in and have a desktop sitting in your web browser where it basically kind of renders the images of the desktop onto your screen. This is also, if you guys have ever used LabSpace at SFSU, that's exactly kind of what's happening in that example. So that is infrastructure as a service. The Amazon example that I gave is a very popular service known as Amazon's Elastic Compute Cloud, or EC2. And this really gives you fine-grained flexibility with your computing resources. You can spin up these instances and do whatever you want. You have super user access, you have root level access, you can do whatever you want with those machines. And then also, when you do that, you have service level agreements that guarantee the reliability of access to that virtual machine, as that can become very, very important, especially if you're using that to develop software applications, for example. You need access to that thing on demand, when you need it, at the times you need it. So let's talk about another type of service, storage as a service, or excuse me, data as a service, which is the theme of storage. So it allows users to store data on remote hardware and access it from anywhere you need. Some examples of this are, relational databases in the cloud, distributed file systems. We have some examples of those we gave in the last lecture. Key value stores, a few of those that give examples in the last lecture. For example, a key value store is Redis. I think that was mentioned on one of the slides in the last lecture. I have another example here, and that's Amazon's S3, which is a prime example of a relational data as a service. And then DynamoDB is also offered by Amazon. I might not have had that in the last lecture. That's an example of a key value store, just like Redis. So let's talk about communications as a service, where communications is actually a very vital component of cloud infrastructure. Guarantees an actual quality of service for cloud computing, and it's very important because it supports some of the following types of things that you would need as a developer of cloud applications, or someone who's reliant on different types of services in the cloud. So it supports things like network security, dynamic provisioning of resources, of communications resources, such as dedicated bandwidth. You want to be able to provision that stuff on the fly. Also guarantees the time between message receipts if you have a very time synchronous application. I can think of one right now. For example, Skype or Google Hangouts. You may want to, if you were the developer of such a thing, you may want to guarantee the delay between messages to know when those things are going to show up, to know when you can piece them together and have a continuous stream of communications. That's a difficult task. Communications as a service also provides necessary encryption. Let's say you want to have an encrypted Skype conversation, which I don't know how to do, but I'm sure there's a way. and then also provides, communications as a service provides network monitoring services. So let's move to the second to last type of service, which is platform as a service. And this is also a very popular one, where you have cloud software, which is, acts as more of a platform. You have very well-defined APIs to implement applications and deploy them in the cloud. So the users of platform as a service are usually people who develop against that platform, such as web developers who might use Google App Engines, also web developers who might use Elastic Beanstalk, Heroku, or people who are developing, maybe more customer relationship management oriented applications using something like Salesforce Apex. So the last one we're going to talk about, the last service we're going to talk about is software as a service, where this is the end user's service. This is, it's visible to all the end users of the cloud, and we all use this without research, without even realizing it. In some examples, I'll just go down to the bottom bullet and give you some examples of this so you have some tractability. Some examples are Dropbox, Google Apps like Google Drive, the different apps like spreadsheets, documents, etc., and Salesforce. Just using it as a customer relationship management system. So software as a service is accessed through website portals, where it's attractive to users and developers alike, as it alleviates the burden of software maintenance, upgrades, and support costs. So all the user's data is also automatically stored in the cloud. That makes it very advantageous for people who have to do storage retention, archiving and backup and things like that, because it's already stored in a central location just by you using the service in the cloud. For example, when you use Google Docs, your data is never stored on your machine, just enough so that it can be rendered for you to update and edit. But that data, it's saved on Google servers. So we all benefit from cloud computing and the different types of services offered by the cloud. Right now, it's probable that most of you are only benefiting from software as a service, but maybe when you go out into the working world, you'll benefit from and maybe have to use in one form or fashion the other types of services that are available. So let's conclude here and talk a little bit about where we've come and kind of the philosophy of how I've guided this lecture. We talked first about physical hardware, and modern computing has transformed physical hardware into virtual resources, with the exception of the computers that you're using to watch this presentation or do things for this class or your other classes. Physical hardware has been virtualized, with respect to the things that get served to us, like our web applications, like our Google Drive stuff. This is maximized computing resources. It gets rid of that one-to-one relationship between operating systems and physical hardware, and also minimizes server footprints. So this has resulted in a variety of virtualized resources being offered as services over the internet in a variety of ways. And so we talk about those computing resources and the basics of that physical hardware. We first looked at basic computer operations and what they look like when they are virtualized. And then we discussed how computing resources can be distributed to enable massive parallel operations. And the combination of multi-core processors, the hardware aspects, virtualization, and the ability to spread a particular task over multiple servers, whether they're virtualized or physical, gives rise to this notion of computing as a utility or cloud computing. And so what I hope is this helps you understand the progression of computing and where it's gone, how it's gone from physical to largely virtual when it comes to the applications that we use, that I'm using right now, and helps you understand how they look in the current IT landscape and gives you the tools that you need to help with your project, of course. And when you go out into the working world, you're rather familiar with what goes on underneath the hood with respect to the computer that you might be using now, and or the different types of web applications that you use for a number of different reasons. So that's it for now. Until next time, have a good week. I will see all of you if you're in my Section 11 class. I will see you on Wednesday, and we'll have a case study that we'll go over that I'll also post with some questions. And if you're in my Section 12, I'll see you on Thursday, and we'll be doing the same thing. So, have a good week, and I will see you later in this upcoming week.